Okay, so it is already 7 o'clock, right? It is already 7:02. So let me start. Today, what I'm planning to do is first let us start with a bit of a asymptotic Bode plot, which I told you long back. And after that, I will give you sums. Okay, three sum I will be giving you. But before that, let's start with asymptotic Bode plot. Okay. What about the other people? Their attendance is again so low today because of the festive mood, or what is the reason? Any idea, Anubhav?
So, sir, because of festival.
Okay, okay. So this topic, I thought that you take time to cover this. This I thought was important, but again, nobody has come up. So, okay. Anyways, okay. Let me share my screen, right? Okay. Okay. So, what we can see over here is this. Okay. Leave it. So now you can see this transfer function, right? Gs divided by 1 plus s divided by omega 0. Can you see the screen?
Yes, sir. Yes.
Okay. Okay, so let me tell you the basic idea behind this this asymptotic Bode plot. Okay. So the basic idea is you have to draw the plot in such a fashion so that at omega I mean at the asymptotes, or the if you look at the real Bode phase plot, you will see that it would be following this asymptotic Bode plot when omega is far away from this corner frequency omega 0, or omega this it is far less than the corner frequency omega 0. Just a minute, maybe there is some kind of a problem over it. Let me use the EA itself, the PDF version of it. Okay, just a minute. Okay. So what do you have to do to find the phase of this transfer function? That is minus of tan inverse of omega divided by omega 0. So we see that when omega is much less than omega 0, that the phase of this transfer function would be 0. So the plot would start from 0. The phase plot would be starting from 0. You see, when omega is less than 0.1 omega 0, it is 0. So the real plot would be is marked by the dashed line, and this is the blue solid line you see is the asymptotic Bode plot. Okay. So at omega, when omega is far more than omega 0, what is the phase that this single pole contributes? Maximum phase contributed by a single pole is minus 90 degree. So when omega is much higher than this corner frequency omega 0, you see that the phase would be minus 90 degree. Okay. And when omega is equal to omega 0, if you put omega equal to omega 0 over here, what do you get is the phase would be minus 45 degree. This is what you see in the Bode asymptotic phase plot. So what is the slope of this line? Slope of the line is minus 45 degree per decade. So whenever there is a pole at omega equal to omega 0, you will find that the Bode asymptotic phase plot would fall in this fashion. Now from where to where would you take? So if this is a corner frequency, 10 times lesser than this, the pole would start showing its effect. This is a kind of approximation. You can put this as 0.1. You can see it is very close to 0. It's kind of an approximation that we use. So when the frequency is 10 times lesser than this omega 0, the effect of this pole in the phase plot starts appearing. You see, it starts appearing from 0.1 into omega 0, and then where would the effect of the pole start vanishing? It is about 10 times of omega 0. So tan inverse of 10, if you find, you will see that it is around 89 point something. So we approximate that to minus 90, and we say that the effect of the pole becomes, the effect of the pole lasts from 0.1 to 10, and after 10 times of that corner frequency, the phase remains fixed at minus 90 degree. Okay, so the asymptotic phase plot would look somewhat like this, and the real phase plot would be as shown by the dashed line. So at this point the error is minimum, while at this point at this point the error would be maximum at 0, but omega by 10, omega 0 by 10 and 10 times omega, this point your error will be maximum. The error is around 5.7 degree. Okay, so this is one thing that you have to keep in mind. So when you are drawing the asymptotic Bode phase plot, you keep just one thing in mind. Whenever there is a pole 10 times at frequency less than 10 times of that corner frequency, that is omega 0 divided by 10, the pole will start showing its effect, and the effect would again, not go away, but the phase plot will become flattened out when it is 10 times of omega 0, 10 times of corner frequency. So if there is a single pole, the slope would be minus 40 of degree per decade, as you can see over here. You can see, so what we have seen is when omega is far greater than omega 0, the phase settles down to minus 90 degree. When omega is far less than omega 0, the phase is almost about 0 degree. So if we do the slope, that is 0 minus of minus 40 of degree divided by this log of 0.1 omega 0 minus log of omega 0, you will see that it is minus 40 of degree per decade. So whenever there is single pole, it will be minus 40 of degree per decade. Okay. Now let us see what happens when there are two poles. So if there are two poles, so what would happen to the phase when omega is much less than omega 0? So the phase of this transfer function is given by this expression, phi equal to minus of 2 into tan inverse of omega by omega 0. So you put omega equal to 0, you see that it is 0 degree, right? You put omega equal to omega 0, you see that phi equal to minus of 90 degree. When omega is much greater than omega 0, that is tan inverse, that is omega is tending to infinity, you find that it is 2 into pi by minus of 2 into pi by 2, that is minus of pi, so minus of 180 degree. So again, the effect of this pole would again start from 0.1 omega 0. It is starting to fall from 0.1 omega 0. At omega 0, you would find that it is minus 90 degree. The error is minimum over here, or the error is 0 over here, and from and the phase at 10 of omega 0, 10 times the corner frequency, you will find that the phase becomes minus 180 degree. Okay, so the slope in case when there are two real poles, if there are complex conjugate poles, then it is not accurate. But when there are two real poles, then you can say that the slope would be falling at the rate of minus 90 degree per decade. What would happen if there is a complex conjugate pole? Anyone from the audience? Anubhav?
Yes, sir.
What would happen if there is a complex conjugate pole? I just told you that when there are two real poles, the phase plot would fall with a slope of minus 90 degree per decade. Right?
Yeah, if the complex pole is present, we multiply j, so that j minus 0, the imaginary terms become real, we add it to 1, and the real term becomes imaginary after multiplying with j.
No, my question is, what would happen to this phase plot? Have you understood till now whatever I have said? Have you understood, or should I repeat? Have you understood that?
Yeah, I got that, yes, sir.
Okay. So what I'm asking is, see, I have assumed that there are two poles and both the poles are The real poles. That is what I have assumed. See, S by omega 0 whole square I have said. So there are two poles at omega 0, and I am saying that the slope will fall at a rate of minus 90 degree per decade. Right?
Yes, yes,
So now I am asking, so when there are two real poles, that means zeta is critically damped, zeta equal to 1, right?
yes, yes.
So when it is critically damped, this plot is fairly accurate. But if it is not critically damped, it is under damped. In such a case, when zeta is less than 1, what would this phase plot look like? Would it be same or would it be something different? What would happen to this phase plot?
It would be different.
How different would it be? How will this even if there is a even if the zeta is less than 1, phi at omega much greater than omega 0, it will be minus 180 degree, right?
Yes, yes.
At omega much less than omega 0, it is also 0 degree. Then where would be the difference be? Where is the difference then?
Sorry, sir. Difference will be seen in magnitude plot when we plot magnitude with respect to frequency.
I'm talking about phase plot. What
Yeah,
difference?
yeah.
What
No
difference would?
difference. No difference. I
No
think no
difference.
difference.
Okay, no difference. You are saying. Anybody else?
Sir, in the slope,
So what changes are you expecting in this slope? Navkirti, you are muted. I cannot hear you.
uh, sir, slope,
Yes, you are correct. There will be change in the slope. You are correct. Can you be a bit more specific? Would it be more, the slope would be much higher or it would be lesser?
sir, it would be much. So it will be not shift toward a straight line in opposite direction.
What do you mean? Opposite direction? You are saying this kind of slope?
No, sir.
Then this one?
So, it will not go toward like 90 degree, but more towards 180 degree, a flat,
So at
not
180 degree,
entirely flat, but there will be a change, like more tilted towards 180 degree.
more tilted. You are saying the curve would be somewhat like this. Are you saying like this? Look at the flow of my cursor. Are you saying that the curve would be somewhat like this? What are you saying?
So
Are you saying? Uh,
I'm trying to say that the error will increase in that kind.
the error would increase. I'm asking what difference would you see in this curve? What difference? This is approximate curve that we are showing, right? Asymptotic Bode plot is a approximation. We are saying that when omega is far higher than this corner frequency, then the Bode plot would follow this curve. When omega is far less than omega 0, then this our Bode plot would be following this part of the curve. So that is what we are saying. What I'm asking is, in case of when zeta is less than 1, when it is under time system, would there be any changes in this phase plot? You are saying it is slope. Now my question is, what do you think? Will this slope be greater than minus 90 degree per decade or would it be less than minus 90 degree per decade?
The greater than minus 90 degree.
Greater than minus 90 degree. Why are you saying it is greater than?
So earlier it was one single pole, so minus 45 degree, and as the poles are increasing, like two poles at the origin minus. That's why we calculated minus 90 degree. So
No.
from that
See,
logic.
see, here also there are two poles. When there, I'm just saying that the nature of the poles has changed. Number of poles have not changed. The nature of the poles has changed. It is no longer a real pole. It is a complex conjugate pole. That is what I am saying. The number of poles have not changed. The number of poles is still same. It is still 2. Number of pole is same. It is still 2. My question is, why are you saying that it is greater than minus 90 degree? You are correct. It is more than minus 90 degree per decade. I am just asking why are you saying that? What makes you think that it is greater than minus 90 degree per decade, or it was just a guess?
Sir, I just related what you just taught and not, I don't know the exact answer.
Okay, so just imagine, just write a transfer function. Okay, write a transfer function which I am saying. I'm not writing it over here. 1 divided by s square plus omega 0 square.
Yes, sir.
Now tell me, how would the phase plot look like? How would the phase plot of 1 divided by s square plus omega 0 square look like?
Sir, for the angle will be minus tan inverse omega naught 0. So omega naught.
Tan inverse of,
Tan inverse of omega naught divided by 1.
where is the omega term going then? Where is the omega? Omega 0 is a constant. Omega 0 is a constant.
Okay, so I divided by omega 0, so s square divided by omega naught square plus
So
1.
flat.
Actually, minus 90 degree.
1 divided by s square plus omega square. That is what I am saying. How are you saying it is 90 degree?
So 0 degree.
It will be a vertical line.
It would be a vertical line. Perfect. That was Shahadat, right?
Yes.
Yes. Right. You are absolutely right. Yes. It would be a steep line. That is what happens in resonant pole. Okay. You will find that it goes from 0 to minus 180 degree steeply. It will remain up to 0. At omega 0, there is a steep change. It will suddenly change to minus 180 degree. It will become like this. 0, and then at omega 0 there is a steep change. That is what is a resonant pole. Okay, this is what I call is a resonant pole. That is, there are two complex conjugate pole on the imaginary axis. So when there are two complex conjugate pole on the imaginary axis, that means there is no damping. When zeta equal to 0, the phase plot would look like this. Just see the flow of the cursor on the screen. So it will remain 0 up to omega 0. At omega 0, it will shift from 0 to minus 180 degree, and it will remain at minus 180 degree. You can verify that. You can verify that just by your this
You mean complex conjugate poles with no real part, right?
complex conjugate pole with no real part.
Yeah. If there is a real part, that will not be there.
Yes, that is why I told you s square plus omega 0 square. That means
Okay.
there are complex conjugate pole on the imaginary axis with no real parts. So why did I say that? To make you understand that when zeta equal to 0, the phase plot is something like this. When zeta equal to 1, the phase plot is something like this. So when zeta is varying from 0 to 1, the phase plot would be something like this. It is becoming steeper and steeper. Are you getting the point what I am saying? Can you see the cursor that is moving on your that is moving on the slide right now?
Yes, sir.
Yes.
So at what did I just say? When this is the case, when zeta equal to 1, that is repeated pole over here. That means zeta equal to 1, it is a critical damping condition. In case of critical damping condition, the slope of this asymptotic Bode phase plot is minus 90 degree per decade. When zeta equal to 0, that is no damping, zero damping is there, that is the poles are lying on the imaginary axis. In such a case, you will see that the phase plot becomes something like this. It will remain 0 up till omega 0. From omega 0, there will be a steep change. From omega 0, it will suddenly change to minus 180, and there will be, after that, with higher frequency, it will remain at minus 180 degree. This is your resonant condition, or this is what we call as the resonance. So in case of, if you pick up a simple RLC circuit, what happens? What happens over there is that when frequency is less, it is behaving as a capacitive network. When frequency is high, it is behaving as an inductive network. So what is happening over there? There is a steep change in. So from plus 90 to minus 90, there is a steep change at omega equal to the resonant frequency. So that is what you are observing in series RLC network also at resonant frequency. I am saying there is no damping, so R equal to 0 in that case I am saying. Okay, so this Bode asymptotic plot is fairly accurate when there are real poles. When there are complex conjugate poles, you cannot say, because you do not know. I mean, the slope will depend on zeta, the damping. So you cannot, quantify that by your approximation. Okay, so this is the basic idea. Okay, now let us look at what is the effect of a zero. In case of a zero, again you go through the same process. You put omega equal to omega 0 over here. You will find that phi equal to 45 degree. This is plus 45 degree. When omega is far greater than omega 0, the angle will be minus 90 degree, and when omega is far less than omega 0, the angle will be 0 degree. So the phase plot will be rising from 0 to 90 degree, and the slope would be 45 degree per decade. So what all we have learned, when there is a single pole, the slope would be minus 45 degree per decade. When there are double poles, double real poles, the slope would be minus 45 degree per decade. When there is a single zero, the slope is 45 degree per decade. Similarly, when there are two zeros, you will find it will be 90 degree per decade. Remember that at omega equal to omega 0, this is the corner frequency, the error is minimum. So when you are doing, maybe if you are doing some experiment, then this kind of information is very much useful for you. So how would you find out? I mean, see, when you are doing some experiment, you don't have all these asymptotic Bode plots with you. You don't have all these Bode plots. What you have is the real Bode plot, and from real Bode plot you have to do something so that you come up with this asymptotic Bode plot. You can approximate that, and you can say that the poles of the system lie over here, the zeros lie over here. So those are experimental stuff. Those you have to keep in mind. These, since it is an exam and you are given all these mathematical models, but when you are conducting some experiment or you are doing some research, this kind of this asymptotic Bode plot would not be there with you. You have a system, you would find its frequency response, you will change the frequency, you will see what its magnitude and phase is, and based on the information that you have got from your experiment, from your frequency response experiment, you have to find out where the poles and zeros lie. And see, in case of when you are doing experiments, even if you are looking at the magnitude plot, you see the plot is not going to remain at 0 or some constant value. It is going to fall, but we are approximating that. We are saying that it is almost constant. There is fairly no change in value. Those are approximations. So if you are asked to find corner frequency, if you need to find the corner frequency or you need to find the pole of the system, you need to know how would you find that? If I'm giving you a Bode plot, original Bode plot, and I ask you to find the corner frequency of the system, how would you do it? Anubhav, any idea? Any idea, Anubhav or Shahadat? Yes.
The phase changes.
Any other method?
So, for example, if the transfer function is 1 over 1 plus s over t, then 1 by...
No, the transfer function is not available to you at all. You don't have the transfer function. You just have a actual Bode plot of a system. I am asking you to what the transfer function is. You have to find out the transfer function. You have to locate the poles. How do you locate the pole from a actual Bode plot or actual magnitude, Bode phase plot and Bode magnitude plot? How do you find the poles of the system from actual magnitude plot and actual phase plot of the system? That is my question.
From magnitude plot, when the slope changes by minus 20 dB per decade, then there is one.
That will not happen in magnitude plot at all. Those are approximations that you are making. You are saying it would be a straight line, but this straight line, how do you do that? See, you have made an approximation when omega is far greater than omega 0. This would be true when you are far away from the corner frequency. So the actual Bode plot doesn't look like this at all. Shahadat, any idea?
No, sir.
I have already told to see what you would do is you see that at what frequency the gain is. Say if it is a second order pole, okay, if there is second order pole, so you would just see at what frequency the phase is minus 90 degree. You know that the actual Bode phase plot, and asymptotic Bode phase plot may be different, but at this point the error is 0. So what you do is you simply check what is you see the sinusoidal response. You see that whether the phase difference between them is minus 90 degree or not. That would be your corner frequency. Any other method that you can think of? Have you heard anything about the minus 3 dB, error or something?
Yes, sir.
Okay, so how would you do that then? When does that happen? Minus 3 dB error
At corner frequency.
at corner frequency. So how would you find that minus 3 dB? You have to subtract minus 3 dB from some value. How do you get that some value?
From wherever the Bode plot starts.
Yes, you have to go to very low frequencies. You excite the system with, say you have a function generator, and you set the frequency to very low values, and then you plot the phase. Imagine this is a magnitude plot. Okay, do not think that this is a phase plot as of now. So say what I do is I take a function generator, I set the excitation frequency to very low values, and then I find what magnitude we are getting at the output. Okay, and then we put that we just plot that on the semi-log graph paper. We draw a straight line saying that okay, this would be my the magnitude plot at very low frequencies, and from there you see the actual Bode plot, and you subtract minus where from at which point the difference between these two, the straight line and this actual Bode plot, is minus 3 dB. That point you can also consider as your pole. That is another method of doing it. Okay, these are two methods I'm suggesting. You may think of many other methods. I'm just suggesting because this would be very useful for you. We do the experiment. So when our first course that we take, power electronics and all, there you have to do small signal modeling of buck converter or boost converter, but you don't have the transfer function. What you have is the converter itself. Now what you have to do is you need to excite the system. You need to use a function generator to do a small signal disturbance, and you have to check what the output you are getting, and then you have to plot the Bode phase plot, magnitude plot, and then you have to identify where the poles of of the system lies. Once you identify that, then you have to validate it by your calculations, by your mathematics, the small signal averaging model that we do. So that is one thing. These are some key points that I'm telling you. This will be taught to you, at higher levels, or when you will be working with this kind of stuff. But these are things that you should know. Okay, so I have talked about first order 0. So let us look at what happens in case of second order 0. Similarly, in case we have seen that for a first order 0, the slope was 45 degree per decade. So with every decade, the decade means the frequency is increasing by 10 times. So 0.1 to omega 0 is 1 decade. So in 1 decade, the phase plot will change from 0 to 90 degree. That is what 90 degree per decade means. So when we are moving from 0.1 omega 0 to omega 0, we are moving by 1 decade, and the phase will move from 0 degree to 90 degree. Similar derivation which I have done before. So this, when omega is far less than omega 0, phi would be 0. When omega is far greater than omega 0, then phi would be 180 degree. When omega equal to omega 0, phi would be 90 degree. So similar derivation, but the key point is when there are two zeros, the slope would be 90 degree per decade. Okay, it will so the effect of the 0 will start again from omega 0 by 10. and it will last from 2 till 10 of omega 0, and it is starting from 0 degree. It is starting from 0 degree. It is moving up with a slope of 90 degree per decade, and at 10 times omega 0, it flattens out at about 180 degree. This is what the basic logic of Bode plot is. Okay. Asymptotic Bode plot is. Asymptotic Bode phase plot. Okay, so the error is maximum at this point, this and this point, this at this omega 0 by 10 and 10 times omega 0, the error is maximum, but error becomes minimum at this corner frequency omega 0. Okay, so what would happen when there is a single pole or a single zero? So what would happen if there is a single pole? It contributes to a phase of minus 90 degree, so it will be constant minus 90 degree. So when there is a single zero at the origin, the phase will be constant at 90 degree. Okay, so these are simple. Now let us look at an example. Okay, so let us look at an example how to go ahead with this sum. When this kind of sum appears in GATE exam, how would we do this sum? See, so this is a transfer function which has been given to you. There is 1 0 at the numerator. There is 1 0 at origin, and there are two poles. One is at s equal to minus 1, another is s equal to minus of 100. Now you are asked to find the Bode phase plot. Okay, this is what you are asked to find. See, when there is a 0 at origin, so the phase would start from 90 degree. The phase is starting from 90 degree. Then we have a pole at s equal to 1. So the effect of this pole will start from 0.1. How long will it last? Around 10 times of this omega 0, 10 times of 1, so 10. So during this interval, it will be falling by minus 45 degree per decade, because if there is one pole, it will be falling in minus 145 degree per decade. What would have happened, say, if there is another pole over here whose, say there is another pole over here whose 10 times, say omega 1 is the pole over here. So omega 1 by 10 is lying somewhere over here. So how would the phase plot look like? Anubhav?
Yes, sir.
I am saying that, say there is a pole close to this point, say close to 10 there is another pole. How would this phase plot look like? Would there be any change?
Yes, sir.
What would happen?
minus 90 dB per day.
Yeah, close
Exactly.
to minus 90.
Right. So it would not 90 degree, minus 45, minus 90. So there is already a slope of minus 45 in this region. You are adding another pole. So minus 45, minus 90 degree. Okay, so that is minus 135. What is that? Minus 135 degree per decade. So between this region, it would be falling with a slope of minus 135 degree per decade. Once it moves away from this 10 times of 1, it would again become minus 90 degree per decade, because the effect of this pole has gone away now. Have you understood what I have just said? Anubhav, Shahadat, have you understood what I just said?
Yes,
Did not
sir.
get it.
Shahadat,
No, I did not get it.
you didn't get it?
No.
Okay, so I am saying that, see, the effect of this pole is starting from 0.1 and it is lasting till 10, right?
Yes.
So if there is another pole, say very close to 10, say over here, so it is like, say suppose at 20, as s is equal to 20 minus 20, you have another pole. Okay, so if there is a pole at s equal to minus 20, the effect of the pole will start from what frequency?
Mm,
2, and
10 per 2.
last till
200.
right. So see, 2 is lying somewhere over here, right?
Yes.
So the effect of this, the another pole that I've added, will start from here. So up till now you are falling with minus 45 degree per decade. The moment you get to a frequency omega equal to 2, the effect of another pole also comes into the picture. So the effect of another pole is how much?
45.
Right, so it will add up to minus 90. Yeah, you are right. I was actually doing some mistake. I'm imagining this was some second order pool. Sorry. So yeah, so slope would be minus 90 degree per decade. So once you get over this region, so once you reach 10, the effect of the previous pole goes away, and the effect of the pole which was at 20 still remains the same. So the effect of pole continues. So it was minus 90, it was falling at the rate of minus 90 degree per decade. The moment you move away from this point 10, it will again fall with minus 45 degree per decade, right?
Yes.
Yes. Why are we adding these slopes? What makes us, what enables us to add this slope?
Because in phase we add it. We add the phases.
When there are multiplication of complex numbers, the phase is just the addition of those complex numbers. E to the power j theta into e to the power j of theta 2. So e to the power j theta 1 into e to the power j theta 2. The phase is theta 1 plus theta 2. That is why we are able to add this curves that we are talking about. So this is another example, and this I think would cover the concept that I was talking about a few minutes back. So there is again a zero at origin. So the curve starts from 90 degree. There is one pole at s equal to 1. So there is one pole at s equal to 1. The effect of this pole starts from 0.1 and it would last up to 10. There is another pole which is which is at 10. So the effect of this pole starts from 1 and it goes up to 100. So initially I am falling with minus 45 degree per decade because of this pole. Now as we reach this omega equal to 1, the effect of this pole also comes into the picture. So minus 45 and minus 45 becomes minus 90 degree per decade. So the slope rises over here. The moment we cross this 10, this point s equal to 10, the effect of this pole goes away. And I'm not saying that the effect goes away. It becomes constant. So the effect of the other pole still remains because it will last up till 100. So this slope becomes minus 48 degree per decade. And when we move away from this s equal to 100, it remains constant at minus 90 degree. So this is the basic idea behind this Bode asymptotic phase plot. There are hardly any books which covers this. There are very few books. Maybe you would find this in Norman Nice. But if you have understood what I have just said, that would be enough for your GATE examination. This would be enough for your GATE examination. You need not know more than this. Okay, so let me give you some questions based on this. Okay. It is week 11, right? So this is your first question. Let me see if I am recording or not. I'm recording. Okay. So this is the first question. So you need to find asymptotic base with k and p positive. You need to find the value of this pole p1. So I would give you 3 minutes. I hope you have understood what I have just taught. Just try to do the sum and tell me what you are getting. Please try to do it a bit fast because we are left only with 15 minutes. Anybody with the answer yet?
Sir, 100.
No, it is not 100. Now, Kirti, why did you say 100?
Sir, I just tried to utilize the technique that you just gave, that before 10 and after
So
10.
see, there is a change of change of slope from 0.1 to 10, right?
Yes, sir.
See, there is one pole at 0.1. So at 0.1, there is a pole. So the effect of this pole starts from here, 0.01, and it should last up to 1. So the slope should have been like this, but the slope has increased. That means there is some pole nearby. When the slope has increased, that means there is some pole nearby. Now look at the other pole that we have, 10. Okay, 10. So 10 is over here, and this is the s equal to 10 point, and we see that from s equal to 10 to s equal to 100, the slope is again minus 45 degree per decade. Okay, it is again minus 45 degree per decade. However, when the slope is when s equal to 1, so where the effect of this pole starts from s equal to 1 and it lasts up to 100. But you see that when you are exceeding s is equal to 10, the slope is minus 45 degree. Whereas when you are somewhere in this region, when s equal to 1 to 10, you see that slope is minus 90 degree per decade. So there must be some pole over here, right? That is what the logic says.
Yes, sir.
So this is 1. So how are you saying 100? Are you getting my point, Navkirti?
Yes, sir, I got it. I just confused 0.01 and zero point 0.1 between these two. That was a confusion.
Practice more, Navkirti. Practice more. You are getting confused very often, so you have to practice much more, I think. And try to practice by giving test series, not just simply sitting and solving. Test series, you have a time pressure, so it would it will train your mind to think very fast. I know mistake happens, these
Yes,
mistakes
sir.
would have been done. I would have done same kind of mistakes, but when you practice, you will gradually overcome all these challenges. So is it clear, Anubhav or Shahadat? Do you understand what logic I am saying, or will I
Yes,
repeat?
yes,
You have understood why P1 I am saying it will be equal to 1?
yes, yes. The angle phase changes at point one. So the pole is at one, so its effect comes at point one.
You're right. So you see that there is a change in slope. There's an increase in slope over here. So slope increases by 90 degree in one decade. So there certainly has to be. So if there is only one pole, it would have been minus 45 degree itself. So it would have gone to minus 90. Whereas it has come down to minus 35 degree. That is, the slope is minus 90 degree per decade. So there must be one pole over here, or else there is no other way out. Again, when there is 10, when there is a pole at s equal to 10, in that case, this the effect will start at 1 and it would fall at a rate of minus 45 degree per decade. But you see, it is falling at a rate of minus 90 degree per decade, and then this effect goes away over here, and this pole becomes dominant. So this pole has the effect over here. Is it very clear, or should I spend another class on this? What do you think?
So in next class, if you have time, please discuss Nyquist criteria.
Okay, okay, okay. I would prepare some notes for that then. Okay, okay, I will do that. But this concept of asymptotic body plot is clear.
Yes, sir.
Yes, sir.
Okay, okay, good. Shadat, is it very clear, or am I not able to convey you the message?
Yeah, it is clear. But I did not understand that capacitive and inductive part that you are talking about.
Okay. Uh,
At
so
the
what?
end, if you can explain that. Yeah.
Okay. So if there is, so you can you draw a series RLC circuit? Series RLC.
Yeah, I have drawn it.
How would the impedance plot of the series RLC look like with variation of impedance plot with frequency? How would it look like? Any idea?
I'm trying to figure out.
Okay. Others can try this sum. These are again very simple sum. You just need to find the transfer function. This will hardly take you 1 minute or 2 minutes to do it. Shahadat, you can continue with that RLC circuit. Let others do this. Shahadat, did you get what the plot of impedance plot look like?
Oh, give me some 10 more. 1 minute more. I'll get it.
A, sir, A.
Okay. Now, Kirti, what are you getting?
Sir, B.
B. Okay. Let us see. So I'm converting this into a single block, that is G3. And G3 will be G1 divided by 1 plus G1 into H. Simple transfer function that we already know. This you can consider this as a single block, and you can reduce it in this fashion. G1 divided by 1 plus G1 into H1. This should be H1. I have written H, so forgive my mistake over here. So now you can consider G3 as a single block and G2 over here. And we again do the same operation. G2 into G3 divided by 1 plus G2 into G3. So if you do that, you are going to get this answer. That is G2 into G1 divided by 1 plus G1 into H plus G2 into G1. Good enough, Kirti, you are correct. So the next sum.
Yeah. So,
Yes, Shada, tell me.
yeah, I have plotted its magnitude of the impedance versus omega.
Yes. So how are you getting it?
So
Can you share?
it
Will you
starts
share
at
this screen? or will you just
Mm,
say?
yeah, I'll just say because.
Yes, yes. Tell me yes.
So it will start at some high value, come to zero, and again go back to some high value.
Correct. Absolutely. So if there is a resistance, if there is a resistance in series with this L and R, L and C, so that low value would be R, right?
Yes.
Mhm. Okay. So if the low value is R, so when there is a resistive circuit, what is the phase between the the input voltage and the input current?
In phase.
In phase. So phase difference is zero, right? Shahadat, are you getting my
Yes.
point?
Yes.
So initially, what is the impedance? J into omega L minus of 1 divided by J into omega C, right?
Yes.
So when omega is very small, what is dominant? Which of the factor is dominant?
Real part resistance.
What is dominant?
No, are you asking about omega L minus omega 1 by omega c term? Or?
No, I am saying that I'm saying that Z of omega is equal to J of omega L minus of 1 divided by J of omega C. I am saying that when omega is very small, which of this term is dominant? Omega L is dominant or 1 divided by omega C is dominant?
1 by omega c.
So initially, if you look at the circuit, it would behave as a capacitor.
Okay.
When omega is very high, how would it behave? It will behave as a
Inductor.
right. So when it is behaving as a capacitor, what is the phase difference between the current and the voltage?
0.
When it is a capacitor, what is the phase difference between the voltage across the capacitor and the current flowing through the capacitor?
It should be minus 90.
So the current would be leading the voltage by 90 degree, right?
Yes.
In case of inductor, what is the case? What is the phase relationship between the current and the voltage?
Current will be lagging by 90 degree.
The current would be lagging the voltage by 90 degree, right?
Yes.
And at resonant frequency, the current is in phase, right?
Yes.
So how is the phase changing? It is changing from 90 degree to minus
0
90
to.
degree,
Yeah.
right? You are getting my point?
Yes.
So this is exactly what I was telling you. So say if there is no resistance, okay, if there is no resistance, the phase will suddenly shift from 90 degree to, plus 90 to minus 90. What is that? Oh, I have closed that. Okay. Oh, lost a minute.
Okay. I got it.
You got the point, right? That is what I was saying. So, so up to omega 0, when frequency is less than the resonant frequency, the phase would be plus 90. So it is not drawn over. I'm just saying. I'm just telling you how the nature of the plot would look like. So it will remain at plus 90. At omega 0, it will suddenly shift to minus 90 and stay like this. So initially it would be capacitive because the current is leading, and then suddenly, just when you just shift a little from this resonant frequency, it will drop down to minus 90 degree. You got the point, right, Shahadat? You have understood what I'm saying.
Yes.
There are several questions based on this in GATE also, I think. Yeah, there are several questions as far as I can remember. There are several questions based in 1 year. It came as far as I can remember. Maybe in my set only it came. So which question was I showing? There was another question to solve, right? This is week 11. Oh, I've already opened that, I guess. Okay. This was the one. Okay. This is another very simple sum. You can directly say it from the EA itself. So what is the steady state error of this? Yes.
A.
Right. Right. Correct. Yeah. Yes. So yeah, Navkirti, what do you think?
0
Why is it zero?
because type is equal to 1.
These are mechanical ways of saying the answers. Okay, type equal to 1 is a mechanical way of saying it. See, the basic philosophy, you try to understand why do you say that. See, so if you look at the this es is error function. Okay, e of s. So u of s equal to c of s into e of s. So e of s equal to u of s divided by c of s. U is the output of this block, of this controller block, and c of s is the impulse response of the controller. Okay, so if I want e of s to be 0, then the value of this should be very high. Cs should be very high, right? Correct?
Yes, sir.
Yeah, Navkirti, did you get what I'm saying?
Yes, sir. Sir, but can you repeat once again?
I'm saying that. So what is u of s? U of s equal to c of s into e of s. This how you have understood?
Yes, sir.
Okay. So what can you write e of s? E of s equal to u of s divided by c of s. This you have understood?
Yes, sir.
So if I want my error signal to be 0, at steady state I want the error signal to be 0. So in that case, there are two possibilities. One is u of s equal to 0, that is the controller output becomes equal to 0. Okay, but if the controller output becomes equal to 0, there is no feedback. It becomes open loop operation. So the only possibility is c of s equal to 0, right? C of s equal to infinity, right?
Yes, sir.
Right? So that is why we actually want, just a minute. That is why we want this gain of this controller or gain of any block that we are using as a controller to be very high. So we want that this gain, if this gain is very high, then the error would be tending to 0. Okay, so in case of an integrator, for DC values, for tracking DC values, what is the gain? What is the gain when you are trying to track a DC value? A of s.
A.
A of s, replace s by j omega.
A by omega,
A by omega, at omega equal to 0, what is the value?
infinity.
Correct. So that is why we say when I am using an integrator, the gain of that function at DC values, at small frequencies, becomes infinity. That is why we say that the steady state error is 0 if I am using a integrator. Did you get my point, Navkirti?
Yes, sir. Now I got it.
Okay. So see, any transfer function you use or any controller you use, the gain will not remain constant for all frequencies. It will definitely go down. In practical system, it will definitely go down. It will certainly have some dynamics. Okay. Now the question is how to design a controller. You have to see what disturbance reduction I have to make, what signal I have to track. When I am saying that I have to track a DC signal, that means the gain of the controller at that frequency should be very high. Say I am saying that you need to track a sinusoidal signal of 0.1, omega equal to 0.1 radian per second. So you have to ensure that the gain of the controller at that frequency at omega equal to 0.1 must be very high. So one possible way of doing it is adding a resonant pole over there. So if there is a resonant pole, that is A divided by S square plus 0.1 whole square, then at omega equal to 0.1 whole square, the gain becomes infinity. In that case, you can perfectly track that sinusoidal signal I am talking about. Are you getting my point?
Yes, sir.
Shahadat,
Yes, sir.
you understood what I'm talking, the resonant thing I'm talking about. Did you understand?
Yes.
So if it was a divided by s square plus omega 0 square, and you were asked to track a sinusoidal signal of frequency omega 0, so when s equal to omega 0, you have minus of omega 0 plus omega 0, so it becomes 0. The denominator becomes 0, so the gain becomes infinity. So at that frequency, gain is infinity, and the controller would be able to track that sinusoidal signal perfectly. This kind of control is called internal mode control. Okay, this you'll study maybe at higher studies. So what is the effect of adding this integrator? You see, if you add this integrator, this blue line is the Bode plot of the integrator, this red line is the Bode plot of the plant, and this is the gain crossover frequency. What would happen is, when we add these two transfer functions, the net transfer function would be shown in the dotted purple line. You see the purple line, dotted purple line.
Yes.
So what do you observe? You see that the bandwidth has reduced now. Do you see the bandwidth has reduced? It has reduced from omega. The unity gain bandwidth has reduced from omega g1 to omega g2.
Yes.
So what would happen? So if the bandwidth gets reduced, what would happen? What is the effect of reduction of the bandwidth?
More delay.
Absolutely. The system becomes sluggish because bandwidth is directly related to the fastness of the system, the fast response of the system. If you are reducing the bandwidth, you are actually making the system slow. Why are you saying that? Because you see, you are now, the first thing that you have to understand is, so say suppose there is a DC signal that you have to track. Okay. So if it is a second order system, say you are applying this DC signal to a second order system, the reference input to the second order system is a step input. What would the response look like? Shahadat or anyone? The
So
unit
can you
step
repeat the question?
the unit step response of a second order system, how does it look like?
You mean underdamped?
Underdamped, yes.
Yeah, it will go to a peak at resonance frequency and come back.
Not at resonant frequency.
Sorry, corner frequency.
No, I'm talking about step response. You are
It will decay after some time by just oscillating.
decay to what? Decay to what value?
To the gain of the system.
Right, to the DC gain of the system. Right. So you've understood you know that you know the response of a second order system of a to a unit step, right? So it
Yes.
moves from zero to a maximum overshoot, and then it oscillates a bit and then settles down to the gain of the to DC gain of the system, right?
Yes. Sorry, I was talking about Bode plot. Sorry.
So if that is so, what do you observe is at steady state there is only DC component, right? There is nothing. There are no other frequency components. There is only one frequency component. There is the DC component, right?
Yes.
So where are What are the higher frequency components are? The higher order frequency components appear in your oscillation during the starting of the system. So the starting of the system, you have these sudden rays you will see, and then it oscillates and settles down. These oscillations that you see, so the expression is 1 minus e to the power minus zeta omega n divided by root over of 1 minus zeta square sine omega d into t minus phi. So this oscillation sine omega d into t, these are these high frequency components. Okay, are you getting my point?
Yes, sir.
So at steady state, you are not getting any high frequency component. Your high frequency component manifests themselves during the starting, as a result of which you see the overshoot, you see, slowly it is decaying. All these high frequency components, appear during your starting transient. You understand? You agree to my point? Anubhav, Shahadat, Navkirti, everyone agrees to my point?
Yes, sir.
So now what you have done is, by adding this integrator, you have reduced the gain over here. You have reduced the gain of these frequencies. These frequencies, this, I mean, the one that you see with the double-ended arrow. So these frequencies were responsible for making the system fast. So if there are many, if the gain was high for a certain range for the, I mean, if the gain is high for certain frequency range, for the mid frequency range, if the gain is high, then the system would track those signals also properly. Because for tracking a signal, the key point is to have a high gain. That is the key point. That is what I told in the previous slide. Whatever, what the basic philosophy, if you want to track x of s, the basic philosophy is the frequency of which the signal is. At that frequency, the gain of the controller must be very high. Okay. Now, by reducing the gain of the mid frequency region, you have actually reduced the gain of those high frequency components which was responsible for making your system fast. You have now reduced the gain of those frequency components. Because of the reduction of this gain of these frequency components, you will see that your system will become sluggish. One way is to look at the bandwidth itself. Simple way to say the bandwidth has reduced, so it has reduced. But if I ask you, if the bandwidth has reduced, so what? So what is the problem if bandwidth has reduced? So the main thing is you are reducing the gain for this range of frequencies. And this range of frequencies, the mid frequency region, was responsible for making your system fast, because these are the one which creates the fast overshoot, and you have reduced that. Okay, did you understand the basic logic?
Yes, sir, but I'll just revise it again.
Okay, then I will. If you are not understanding it, it is already 8:13. I have actually overshooted the time. I understand it is difficult for you people. I will, if you want me to do, I will discuss that in the next class also. Do you want me to discuss it in the next class also?
Yes, sir.
Okay. Shadat, was the concept clear, or what was the, yeah? Is there any problem to understand that?
No, sir, I understood it.
You understand it, right? Okay, thank you. So I have used that, error coefficient Kp to find what the error coefficient is, and sales error is given by 1 divided by 1 plus Kp, that is 0. So the correct option is A, which is very evident from the transfer function itself. But I wanted you to understand this concept. Why are we saying what we are saying? Why are we saying that when there is a single pole at 0, the steady state error would be 0? Why are we saying that? That I wanted you to understand. That is why I drew all this plot, so that you have a clear picture of what is actually happening. So the integrator, what the main function of the integrator is that it makes the DC gain very high. But in order to make the DC gain very high, the price you have to pay is you reduce the bandwidth of the system, thereby making the system sluggish. You make the system slow. And this is the reason why we do not generally tend to use, generally do not go for integral, we go for PI controller. So in case of PI controller, what you do is you add a 0 over here and you flatten out this curve. So if you add a 0 at this point, at this point where it is, so where not at this point, sorry. So if you're adding a 0 at the point where this blue curve is going to negative. So when the blue curve is going to negative, that means it is not adding to this red plot, it is reducing the gain. It is reducing this red plot. So what you do is you add a 0 over here and you cancel out this negative going plot. You make it flat. So the mid frequency region, the gain of the mid frequency region remains same as that of the planned gain, and the response is as per your desire. So that is the main reason why you go for PI controller. You understood why what I am saying?
Yes.
Anubhav, did you understand?
Yes, yes.
Okay. Navkirti, did you understand?
Sir, I'll just need to revise it and then I'll get it.
Okay. Then we will talk about it in the next class. Okay. Then so I gave you one assignment actually. I still was not able to,
Yes, sir.
the decimation and all those things. Maybe in the next class, then I will. Next class maybe would be the last class. I am not sure, because we are actually given for 12 weeks. Maybe next class I would be, maybe it would be go around 1.5 hours or something. I would see your flux lines in the next class then. Okay, is that okay, Navkirti?
Okay, sir. Yes, I have already drawn them.
Okay, okay, okay. Thank you then. Bye bye everyone. Enjoy your weekend and enjoy
Thank you,
happy
sir.
Diwali to
Happy
everyone.
Diwali, sir.
Yeah, thank you.